Next, we have our second speaker, Xinyi Wang. So Xinyi Wang is currently a postdoc at PLI. She recently got her PhD from UCSB, where she was advised by Professor William Yang Wang, received the JP Morgan AI PhD fellowship and the UCSB Computer Science Outstanding Publication. So her research centers on developing a principled understanding of large language models, with the aim of enhancing their capabilities and addressing their limitations. She also interned at Microsoft Research Montreal and MIT IBM Watson Labs. Today she's going to talk about subscaling. Okay.
Thank you for the introduction. So today I'm going to talk about the work I done when I was intern at the MIT IBM AI lab before. So it's about do larger language models imply better generalization for training scaling law for implicit reasoning. So we are all both very familiar with the classic scaling law. So the first scaling law paper is saying that if you scale the compute or data size or parameters, the test loss would also decrease exponentially. And so here the test loss is computed on in distribution for the text that's in the same distribution as the pre-training data. And so in this way, we are able to understand the testing performance of large model based on the trend that's calculated from predicted from only the pre-training smaller. So that has been very useful in industry and right now. And so recently there are also like a lot of different scaling laws proposed by many researchers. So for example, like different we find that actually different skill, different language model skill requires different scaling laws. So this picture is from another paper from the ACL 2025, and so they are so they try to show that basically for language model to perform knowledge related skill, the language and when for language model to perform code related skill, the scaling curve looks differently. And so here, like each of these colored curve from like colored by from blue to pink are model testing laws from the same compute budget but different data and model size. And then so this black line is basically trying to say that the optimal model size for like choose by general pre-training testing set, and the red line is the optimal model size choose by task specific testing side. And from the figure here, we can see that the blue curve and the blue line and the red line doesn't overlap, and also like for knowledge task, the red curve is above the black curve, and for code task, the red curve is below the black curve. And this basically they try to say that like the knowledge task is more parameter demanding, and the code task is more data demanding. And so here in our work, we're trying to understand the scaling of reasoning, or more specifically, we are trying to understand the scaling of implicit reasoning. So we are actually more familiar or used to explicit reasoning, which the language model needs to output a chain of thought to solve a question. Well, for implicit reasoning, we can just understand it as you just do not output any intermediate solution step, but directly output the answer. And so here we can think of the reasoning is happening internalized in the model layers. And so here we are trying to study how this sort of implicit reasoning scale with the language model training. And so here in our project, we're trying to use language model with llama-like architecture. And the laws we're going to use to pre-train with this model is just the next prediction law. And the training data, we are considering construct a training environment that can be rigorously controlled to perform this sort of implicit reasoning. And also, we're going to evaluate on this environment and that can show this implicit reasoning performance. And so to construct this sort of implicit reasoning training environment, we are trying to first take a closer look at how can we formalize reasoning in general. So in our opinion, reasoning can be formalized as connecting the concept A and the concept B that we've never seen together before. And to connect this to concept, we can find basically intermediate concept that can connect A and B step by step. And then finally, we will be able to reason from A to B through this chain. And so here we can construct a reasoning scenario by basically gathering a lot of such reasoning chains. And in this case, this would form a graph. And we can, so in real world, there are a lot of such like concept graph, which can be, for example, knowledge graph consists of 4 knowledge. And usually on this graph, these graphs are usually incomplete. So in the sense, this incomplete missing age, for example, there's no age connecting A and B, but it can actually be reasoned from other ages in the graph. And so based on this observation, we're basically trying to construct implicit reasoning environment from the incomplete knowledge graph. And so in this graph, for each node, we call it an entity, and each age, we call it a relation. And so the training data format here we consider is incomplete knowledge graph, and the data format would be each training example is a knowledge triple, and the entity or relation representation we consider 2 different cases. So one, we just basically assign a random ID to each relation and just making them a 3-number triple. And the other case is that we just translate this meaningful triple into an attribute set. And so here we just do the pre-training on this constructed like text data set from the incomplete knowledge graph. And then for evaluation, we would like to evaluate language model performance on the missing age. So here, so why the language model would be able to infer those missing age from the incomplete graph. So for example, in this scenario, we can see that the language model have been seeing a logic rule, which is in the state plus it's a state implies it's the country. So for example, if it have seen like Princeton is in the state of New Jersey and New Jersey is the state in country of US, then it's also been saying Princeton is in the country of US, then this constructs a training example for this specific logic rule. And so ideally, like in the knowledge graph, there are many such training examples for this logic rule. And so the language model will be able to pick up this pattern and then thus be able to infer this missing link between Rothbard and West.
By the way, there are like a dozen Princetons in the US. Probably.
Yeah, I mean Princeton University. I just didn't put the university there because because the circle is a bit small. Yeah, but yeah, I mean university. So here at the inference time, we just we construct several options for the missing age. So for example, we say the missing age could be relation 1, could be relation 2, and then we let the language model predict the likelihood of each of these relations being the missing age. And then we pick the relation that has the largest likelihood. So here's here's one experiment with real world knowledge graph, which is constructed from freebase, which you can understand as like Google Web.
你说对它是 accurate， 就是对它是 accurate 的关系。I did this.
Yeah, I know that. So yeah, so and then the we report both the reasoning accuracy and the testing loss on the test set. And so we find a reason, like interesting phenomenon, which is actually when the model size is larger, as shown in the x-axis, the performance on the y-axis not always increase. And so here we are using the same data set, just different model size, and different line indicate different number of training steps. So basically more training staff would like amplify this U-shaped curve phenomenon. But as we see, the training loss is steadily decreasing across when the model size becomes larger. So yeah, and so we also actually tested this same thing, but with processing the knowledge graph triple in percentages. So here is just a like incomplete graph, but you can see it's having the same trend regarding the model size and like reasoning performance. So here, so before we are trying to just get a like surface understanding of how like reasoning performance would change with respect to different model size. So here we're trying to do a more systematic experiment for like for holistic understanding of how the underlying training data would affect this scaling curve. And so here we trying to create knowledge graph synthetically. So by like referencing to real world knowledge graph distribution, we have this three key steps of the synthetic data generation. So the first step is that we would generate a bunch of conjunctive rules, just like I introduced before for better generation of the graph. And then we would control possible number of relation types connecting to GPT. So in this way, the randomness of each node branching out would be much lower. And then finally, we grow the graph with preferential attachment to ensure like power law degree distribution, similar as real world knowledge graph. And so after this, we trying to update different hyperparameters in this data generation process with respect to model size and data performance and reasoning performance. So here in the graph A, we are actually trying to understand the effect of training steps on this curve. So if you can see, there's actually the best accuracy or loss is stable across different training steps. And so so here we are trying to, so we are more focused on the optimal model size that a graph, when you train a language model on a graph, can achieve. So this optimal model size is the smallest model size that can achieve the highest reasoning performance. And so it's solely associated with the training graph itself, not associated with the other hyperparameters. And so from graph B to F, we have like different ways of generating the underlying training graph. And so if we're if here we are only focusing on the optimal model size, we can see that more triples and more relations would definitely produce a larger optimal model size. And well, for the number of rules and intractable ratio is not that significant. That's the optimal model size to change. So here, like we do not have a very conclusive prediction of how the optimal model size related with the knowledge graph. And so we would like to introduce a holistic measure of the graph that can be better related with this optimal model size.
So is number of steps proportional to how many times you've seen the data point? I don't understand what training steps mean.
Oh yeah, so it's kind of like the epoch.
It is apples.
Yeah, it's the just linearly related.
Yes, so it's just apples.
Yeah.
That's all.
Yeah. And so here we introduce this graph.
Was there a big difference due to margin function or
Yeah.
how many parts?
So basically we do this just for ablation at first, just using the same data, but train like different steps, and we find that the number of epochs does not, so it does affect the optimal model size when at different steps, but we find that because we want to find like stable signal of the optimal model size for a specific graph. And so basically we want to rule out the affecting factors. So for example, the training factors of how many steps to train. So it turns out like if you train more steps, the optimal model size will just be stable. So yeah, that's why we do this experiment. So yeah, so here we introduce this graph search entropy. So this entropy is defined as the number of nodes multiplied by entropy rate of an infinitely long random walk on the knowledge graph. And so if you look closer in the definition, it has two parts. So one is the entropy degrees regarding entity, and the other is the relation. So basically, if you consider you are doing a random walk on the graph, you have two parts of randomness. One is from the entity assignment from the node, and the other is from the relation assignment from the edge. So if you have a closer look, the first part is the entity and entropy rate part is like calculated by the dominant eigenvalue of the adjacency matrix, and the relation entropy rate is calculated by basically how the relation construct the entropy of the relation transition matrix with regard to the stationary distribution. So yeah, so after we introduce this, and actually we have tried some other options. So this one actually relates with the optimal model size effect. So here we collect like all the synthetic experiment we ran before with their optimal model size, and also we compute the the graph search entropy of each training data, and so we find that it can kind of relate kind of linearly when we use linear regression, and also we find that if we also compute the graph search entropy of the actually 50K data set, it can be predicted by the linear regression produced by the synthetic data. So it's kind of close to the real world. So our graph is kind of close to the real world distribution, so that we can have some real world prediction power. So here I want to introduce a little bit more about how this related to other law, like scaling law. So previously there has been a scaling law proposed by Meta, which is called knowledge capacity scaling law. So in this scaling law, they are trying to measure the data entropy by the knowledge generation process, or just the data generation process. And then they find that the model can remember 2 bits information per parameter. Well, in our scaling law, if you look at the regression line, the per parameter information rate is around 0.008 bits. So this is because, so first we have different way of computing the entropy. So our way of computing the entropy is just randomly traverse a fixed knowledge graph. And also this also hints on that reasoning is far more data demanding than knowledge memorization. So this actually echoes the picture that I showed at the beginning of the talk. So basically, there's another group of researchers find that the knowledge task is more parameter demanding, and the reasoning task like coding is more data demanding. So which is exactly what we find when comparing with the previous work on knowledge scaling. So, and then finally, I want to touch a little bit on the real world implication. Although in this paper we do not actually have the real world to train data to train on and also analysis on, but and like we think it's possible to extend this by just extracting knowledge graph from real world training data set to compute their graph search entropy. And also another implication is that if the current scaling law we found actually holds in real world, then given finite data, a larger model will eventually overfit reasoning data. But however, this optimal model size might be very, very large. So probably we are not reaching that yet. But given that current language model training is more bottleneck by data than by compute, this might happen in the future. So yeah, that's
The synthetic data can be generated from reasoning tasks.
yeah.
And they're good.
But I feel like the performance of the synthetic data is far worse than actual image generated data, if I understand correctly. So, okay.
Yeah, don't believe those people.
I'm wondering whether like, you know, negative log likelihood is a good barometer for some of these tasks. For coding. I mean, I guess for your knowledge graph task, it makes a lot of sense. But yeah, I don't know. I'm just trying to like digest this like scaling law because like it's kind of different than traditional scaling laws, like the chinchilla optimal scaling law. You could overtrain, you just get diminishing return. Here you're seeing like U-shaped curves. Yeah, I don't know. It's an ill-formed question, but can you comment on it?
So we actually have both accuracy and like negative log into log. So they're in almost the same change. So
For this task, yeah, it makes a lot of sense. I guess I'm just wondering for like coding or knowledge tasks whether it makes sense.
yeah, I do feel like they're closely related, but the trend might be different. So for example, if we just want the like end signal, like we want to just evaluate on the correctness of the final answer, then there's a big discreteness of the final like signal. So you cannot measure like how many percentage of the previous like reasoning trees is correct. And that might create, so for scaling law, you usually want to create a more like smooth curve to basically fit on. And for if you use that like discrete signal, it would be hard to do that. But yeah, I think there are some previous papers that's actually using the discrete signal, but for only specific tasks, not for the general like language model.
Could you remind me like why there is a optimum model size?
So basically, if you're looking at the like training performance, there is a point where you reach the best performance, and then when the model size goes larger, the performance starts.
Right, but is there an explanation why that happens?
Or why that happens? So basically, it's kind of like overfitting. So you are more and more like trained to remember the training data.
So in other words, your data does not demand like deeper models. Like, for example, like your data is only like 2-hop like things.
Yeah, so it's very related to the data complexity as we measured in this graph search entropy, it's measuring, you can understand it's measuring the data complexity. So the more complex the data is, the more complex the reasoning in the test set would be. And so that's more like larger model we require to perform this task. And so this linear relationship is trying to build the relationship between this fast model size for reasoning on this complexity of data.
Okay, so the entropy thing takes into account how many steps there is in the reasoning process.
So because the way we construct the knowledge graph is not like we explicitly define like how many hops are there in the.
Okay.
So it's kind of random, but the possible reasoning trees that we can find in the knowledge graph is very related to this structure. And so, that's how we.
So I have a different suggestion. You did not do the ablation where you decide the best number of epochs for the model size.
Yeah.
Right? So the correct ablation is for each model size, you find the best number of epochs, and then which is the best.
Yeah.
It's not that big models are bad with their performance drops. It's just overtraining. I mean, they learn faster.
Okay. So here the idea is that we want to find the smallest model that can already reach the optimal performance on this data. So so here in the
No, but you're fixing the number of training sets, which is a wrong thing because you want to take for each model size the best number of training sets because that's the way the pipeline is.
Yeah. We definitely have so we choose the training step to find the smallest. So you can definitely train like less step, and then you find a larger model will perform better, but the maximum performance.
No, I'm suggesting the number of training steps should depend on the model size.
Yeah.
And the number of because the larger models learn much faster.
Yeah. So if we take the training compute as a factor into the.
Not compute. You mean number of steps.
Yeah.
Yeah. Okay.
Yeah. I mean
Number of steps.
the length of training.
Epochs is what I'm talking.
Yeah. So
Epochs.
So
Yeah.
basically, you train more epoch, you would like in one time.
Like for different sizes, the number of epochs will be the optimum number.
Yeah. That's.
So that's the way you should train. Like, what's the takeaway with this?
So here we are. So for our analysis, we're just trying to like locate where's the minimum model size that can reach the best performance.
Is it the best? I thought it's just different models have the optimum performance at different sizes.
Oh no! So we actually find that the optimal point is kind of
optimal point is optimal performance.
The optimal performance. If you look at the height of this line, they're actually the same. And also here, like if you look at it, so the blue one and this like green one is actually similar. So it's like it's not like larger model we eventually arrive at a much better performance. It's just the best performance would appear at a like earlier stage of training.
Yes.
But if you use smaller model with longer training, you can still arrive at optimal.
Well, they can memorize anything. It's a fixed task, so yes, they can get good.
It's not. It's more like a reading task. So this triple are never saying the training data.
But this is post training.
This pre-training. This is I perhaps forgot to say that it's pre-training from scratch. Yeah, it's pre-training from scratch.
But pre-training on general data or just this data?
Just.
Okay, so then definitely, yeah, there's a lot of confounding in terms of like, it's a fixed graph. If you take, what does it mean to take more data? You're sampling other graphs like this, or?
So I changed the hyperparameters of like basic generation of graph. So there are a lot of hyperparameters to just name the field in this graph. So
I see. So you get a larger graph.
Yeah, I can change the graph structure and stuff.
Yeah. Okay, maybe option.
Yeah.
Okay, so for time reason, let's thank the speaker.